Hello and welcome to the KDD tutorial on AutoML. One of the first things that are worthwhile reviewing when we discuss AutoML is how to do machine learning in general and what the machine learning problems are. So I get the honor to do all the basic things, whereas my esteemed colleagues Xinjian and Jonas will talk about the more advanced topics in AutoML. Let's get started with the basics. So, of course, the first thing that you need is a loss function that you can optimize. And then, after we've done this, we look a little bit at generalization performance and why this matters, and cross-validation and related things. And we'll talk about covariate shift, label shift, adversarial data, and non-stationary environments. Now you might wonder, why on earth am I going to cover all these topics in an AutoML tutorial? Well, part of the reason is that AutoML, while it's very smart, need not necessarily be able to fix all of those issues. So if you use machine learning in Angular and just throw an AutoML system at it, you're not going to get necessarily a very good result out of it. That's simply because, well, AutoML can only be as good as the problem that you feed into it, and you may have to pre-process and adapt it in order to get good results. So this sounds, very abstract and generic. Let's actually dive into it. First thing we should probably do is talk a little bit about which aspects of machine learning we cover. So some of the machine learning problems might be collaborative filtering. So let's say you watch movies on Netflix and Netflix recommends some more movies. And while this is some time ago, and it's clear that if you mix preferences and have multiple users share the same account, well, you sometimes get rather strange results. On Amazon Books, well, actually, there's a pretty good recommendation of other books. And as a matter of fact, I have most of them on my shelf already. Now, you might have something very different in games where maybe you want to do imitation learning. So you basically go and, treat the environment in a certain way. And then you want the agent to learn from your behavior in order to have the agent behave in the same way. Now, if you do this poorly, well, your gaming studio will go bankrupt, which is pretty much what happened with Black and White. If you do it properly, well, it thrives. So this is what happened with Gravatar in Forza, which was one of the algorithms underlying the Xbox. Now, another problem is reinforcement learning, and here you see a algorithm that we developed, P3O, doing rather well on a couple of Atari games. Or spam filtering, where maybe you get some emails, spam and ham, and you want to be able to distinguish the two. One of the earlier ones, and this is actually quite surprising that they were able to do this at the time, was check reading. So around 1995 in Jan LeCun's lab at AT&T, the goal was to build a check reading system that would take a scanned image of a check and detect what the amount and the signature and so on were. And so what you had to do is recognize handwritten characters and also printed ones. It worked surprisingly well. Another area where you may or may not have connected it with classification, well, it's ads, right? If you search for mesothelioma, which happens to be one of the most expensive things you can advertise for in the United States, well, if you click on it, well, basically the system wants to estimate whether you're likely to click on it, and then based on your click probability and also, how much you bid, your ad will show up or not. Okay, well, this is quite generic. Let's dive into some slightly more specific things. Supervised learning. So one of the things in supervised learning, and AutoGluon right now covers only supervised learning, is binary classification. So you might do things like, I said, distinguish ham or spam, or in a more advanced issue, you might have multi-class classification, where maybe you want to make sure that you recognize the corresponding bird and the frog rather than mixing up the labels. Or that in this room there's a dog and a child playing with it and their chair, right? So in this case, it's actually not just classification, but you also want to detect. These are problems that have a much more advanced label structure, but it's quite reasonable to assume that AutoML might still be useful for it. Now, besides classification, there's also regression. You might have a linear regression problem or a nonlinear one, or even sequence annotation, where you have like a gene sequence and you want to find out whether there are introns, exons, and so on. So given a sequence, you might want to detect genes, perform speech recognition, activity segmentation, or named entity recognition, or anything else. Now, sometimes you might actually want to have classification, but in a hierarchical structure, and that's what you get in ontologies. So for instance, if you have a web page, you might want to find out that it's a web page about computers, but not just anything about computers. Maybe it's a graphics card review, an installation website, and so you want to be able to categorize this precisely. Another problem related to regression is prediction. So there, basically, you have, let's say, the stock prices, and you want to find out how the stock price will behave tomorrow. In summary, here are some of the problems that you can quite nicely solve with AutoML: binary classification, multi-category classification, regression, sequence annotation, hierarchical classification, or prediction. Okay, so now that we have this, we might ask the question, well, how to actually go about it. So for that, we need to know about the generalization performance. And what already is somewhat tongue-in-cheek expressed on the slide is the empirical distribution lies. Now, this sounds quite abstract. Let's actually see what this means in practice. Okay, let's say I have a simple classification problem and I want to distinguish cats from dogs. Cute cats, cute dogs, and well, okay, look nice. So I build a classifier and works perfectly. Okay, so at test time, well, maybe a new dog comes along and, well, so that's a classification error. So, well, nothing to worry about. Let's go and build a better classifier. Linear classifier won't do, so I have to use something advanced to deal with Dobermans. And, well, we get that. But, oh my God, now there's a black cat, and that black cat also doesn't do it. So maybe you need something even more advanced. Now, this sounds pretty silly, right? And the question is, well, is this just made up? Actually, no. So here's a picture from a rather famous paper, namely by Her et al. About ResNet. And what they did is they looked at different networks and they looked at the training errors for, different numbers of layers. And then they also looked at the generalization performance. And so it turns out that, well, the training error is lower than the generalization or test error. And that's because, well, it's so much easier to learn the answer for problems where you already know, where you've seen the answer, rather than for new problems. This is the one thing that continuously stumps students when they, take classes, and it's not very surprising that we have the same thing here. Now, of course, you don't just get that for images. You also get that for instance, personal assistants, like if I say, Alexa, please turn off the coffee machine, versus Alexa, coffee machine off. Then in both cases, I mean the same thing. But if I've only trained on proper sentences and then I find out that most people just bark at their personal assistant, well, I might see some strange, surprising effects. So why do we care about this? Well, because we want to minimize the expected risk. But we only have the data drawn from this rather than the actual distribution. So the best thing we can do is we can minimize the empirical risk. And as we all know, this is just an approximation. Okay, this still sounds pretty abstract and mathematical. Let's actually look at that in pictures. So here's some distribution of data, and I go and draw from that some empirical sample. let's say those red bits. Now, those red bits, well, they're quite nice, and if I see both, I can kind of sort of infer that, yeah, probably the orange curve might have led to those red samples. But if I don't have it, well, then it's not so easy. So how can I fix it? Well, the thing that we are going to concern ourselves mostly about is by using a validation set. So in a validation approach, you basically hold out separate data that's not used for training, and then I use that to validate our approach. Of course, I can also use Chernoff bounds, and for instance, this very famous bound tells me that the empirical average and the expected error are very close. The problem is that this tells me that for one specific function that's the case. To make sure that this is true in general, well, I need to use a uniform convergence bound, and of course I'm not going to do this here. So, but why does it work overall? Well, because the validation set was never used for training, and unfortunately quite often people cheat, because what they do is they use the validation set to then actually go and pick their model. So while they technically aren't using the validation set to train their model, they're using the validation set to pick the model. And so effectively, if you were to overdo that, it would amount to, well, basically, again, training on the validation set. Now, let's just look at what this means in practice. So here's our empirical data. I take a subset for training, and then I take the complement for validation. One important thing, if I actually care about being able to estimate the error, because why would let's say I pick observations 1 to 100 as training data and 100 to 125 as validation data? Well, that doesn't necessarily make a lot of sense, because I could have as well just picked the first 25 observations as validation and the remainder as training. And as a matter of fact, that's exactly what people do when they perform k-fold cross-validation. So in the picture below, that looks a little bit like Pac-Man. What I did is I performed 4-fold cross-validation, namely by leaving out 1/4 of the data, and it's a different quarter each time, and then using that for validation. Now, we're actually going to use that later on in AutoML, not just for validation, but also for bagging, because after I have all those models, I could either go and train one overall model on everything, or I could just say, well, I've already got those models that I obtained by k-fold cross-validation. Why not just take the average of all of them and use that? And it turns out that this is actually a very good and robust approach. Okay, so now that we've discussed what happens even in the best of times when the data is nice and independently and identically drawn from the same distribution and so on, let's look at some systemic things that could go wrong on our quest to build a classifier. The first thing is covariance shift. So what actually is covariance shift? Well, let's start again with our cats and dogs, and you go and build a classifier, and this works fine, and let's for the moment assume that there are no Dobermans or black cats around. But unfortunately, at test time, that's not what I'm seeing. At test time, I'm seeing this. So obviously this is silly, because, well, I didn't train on cartoons, cats and dogs. Nonetheless, if I actually were to do that with, let's say, a 2 or 3-year-old, they would quite easily be able to transfer from the real cat to, well, those pictures. Even, this gray oversized beast to the right, I would argue that most babies would already be able to recognize this and go, meow, meow. Anyway, so, this is patently silly, but why would anybody do this? Turns out, actually, a lot of cases. So for instance, in web search, you might train on a page that's relevant for the US market, and then you want to test or deploy this in Canada or the UK, Australia. So I'm not even assuming that this is, not English, but even within English speakers, you may have quite some difference. Or in speech recognition, maybe I train on a West Coast accent and then at testing, while I use a Southern drawl, or maybe a non-native speaker who speaks with a very strong German accent, for instance. So this might be a very difficult thing. Okay, anyway. Or you might have shift in language. So for instance, at training, people might say, well, bring me a soda, and then at test time, bring me a pop. So is this real? Well, actually, for pop versus soda, there is a website. It's called Pop versus Soda. And what they've done is they've actually looked at all counties in the United States and evaluated for each of them whether people call it pop or Coke or soda or something else. And quite unsurprisingly, in the area where Coca-Cola has the headquarters, namely in the Deep South, well, they called it a Coke. Anyway, so this is fine. You might also have similar things for medical. So this is the first thing is actually what happened during training time. Some startup thought, okay, well, they had data from old men with prostate cancer, but they needed data from healthy men. So since they were located on campus, they just went out and took their blood samples. And that's a terrible idea, because the metabolism of 20-year-old men that are healthy is very different from the metabolism of 50 to 60-year-old men, whether they are healthy or not. Right. And so that clearly didn't work. Or you might have in reinforcement learning data gathered with a current policy, but then I go and update my policy so the environment responds differently, and I need to, at test time, respond to that. Or maybe if I have databases at training, well, I use some database that's tuned to the 2017 usage pattern, and then I deploy the database a year later, and of course it's not going to work so well. So let's formalize that a little bit. So what I am assuming is that I have some distribution Q of x and y, where the conditional distribution, as in P of y given x, remains unchanged, but the distribution over the covariates, so the distribution of the things that occur, is different. So for instance, in the web search case, probably fewer Americans will search for Mounties and polar bears, or maybe grizzlies, and maybe moose, whereas in Canada that's a thing. Or for instance, the Canadians might care about more what the Queen does than, let's say, Americans do. So at training time, well, you have some data that's drawn from P of x, and then you minimize the risk, but at test time you end up weighing the performance differently. And so what you can easily do, so it's very simple, well, if I have an integral dq of x times f of x, I can write it times p of x divided by p of x. And so I now only need to take care of that ratio, and I basically need to reweight my training data in such a way that it accurately reflects the test data. So what I have to do, in other words, is I have to find the density ratio. Unfortunately, we don't have one. So what you do is you basically build a classifier that distinguishes between training and test data. That also gives you then a likelihood ratio, and then you apply that, you reweight the data, and it's good. So for instance, what you could use is you could use an AutoML tool to distinguish between training and test set, and then use the logistic regression weights to reweight your data to properly train a covariate shift corrected problem. Now, in some cases, these things don't happen just between training and test set, but they might happen more slowly. Let's say, for instance, thanks to maybe global warming, there are fewer moose in Canada, so people will search less about moose. Or maybe they'll search more about moose because they are really concerned about, preservation and all of that. And so what you're going to get is not just covariate shift, but a drift. And so overall, be careful about cases where your distribution changes slowly, not necessarily one after, not just in discrete times, because unless you go and actually monitor this appropriately, you're not going to do well. So for covariate drift, you're going to have to compute corresponding, time-sensitive weighting schemes. So that's probably a topic for a different tutorial. Now, this sounds kind of nice. Well, does this actually happen in practice? Well, it does, and sometimes people get very upset about it. So let's take something very simple. Let's say this is my training set, and I have, cats and dogs. And then at test time, well, I have a lot of cats, and those cats look even cuter than before. And so the classifier might perform a lot worse during test time because of cute overload, right? So why? Well, let's look at what happens in pictures. So let's say I have, 3 data points. Maybe I have 2 that I use for training and 2 that I might be using for an evaluation. If I solve a simple regression problem, okay, well, I observe those 2 black crosses and I, regress this line. Okay, that's fine. And then, I would quite reasonably predict that, where I want to evaluate it, I'll get this black cross on the bottom. Unfortunately, in practice, I might see this. So that's not very good. And if I'd known that this is where, the data occurs, I would have probably used this regression estimator. So what happens is that, well, the optimal estimate is not in the class of the linear functions, and therefore I can get horribly misled by either incomplete knowledge or simply by the wrong function class, and therefore by minimizing the loss on the training set, I'm actually not going to be able to do anything good on the test set. Now, for, maybe a quadratic function, things might have been better, but what this really means is that I really need to be careful if training and test distribution are very different, because then I will get very surprising results. Okay, so as I already promised, this has some very direct consequences. So for instance, if you look at, let's say, image classifiers, face recognition that are trained on IMDb, but then you want to test on a weird professor, then, well, this is yours truly, obviously, then, you would expect that the error on the test set may be a lot bigger. So there's actually a nice little theorem that you can prove, which shows that as long as the performance is non-uniform over a domain, I can always pick a distribution where things are a lot worse. As a matter of fact, I can always pick a distribution where things are at least as bad as, the error on, the original distribution plus the ratio between the variance and the conditional mean. So that's actually quite a nice result, because it tells me that unless you have uniform performance, you can always find a biased test set where the performance will be worse. Okay. Sometimes people have used that maybe out of surprise, maybe with a little bit more intention, for instance, for face recognition, where if you try to insert faces that look very different from what a classifier or a recognizer was presumably trained on, was going to work a lot worse. And this little theorem tells you, well, you can always do that, and not just for faces, but also for any other classification or regression problem. In short, testing where we have insufficient amounts of training data may yield strange results. Okay. Now, in some cases, we have a much simpler problem, namely label shift. And so you might ask, how do you fix label shift? And first of all, what is it? Well, let's say this is my training set, and again, I built this classifier But then at test time, well, I get a lot of cats. Okay, so why would anybody do this? So for instance, medical diagnosis, you might train on data with few sick patients, and then I test on data during flu season where the prevalence is much higher, or I build a classifier for COVID-19 and then I deploy it, and suddenly I get a horrible spike because nobody wears a mask, and then suddenly, of course, my classifier will do worse. Or I train a speech recognition system, and then I train it on newscasts before the election. Then after the election, unfortunately, new names and red hats and other stuff like that are prevalent. So people still speak English, but they talk about some very different, strange things. And so you might have, considerable label shift. So it's still English, it still means the same, so you can still transcribe it, but the topics are now completely distorted, right? So what this means in math is that if you have some distribution Q of X and Y, where Q of Y is different from P of Y, but P of X given Y is still the same. So this is different from what we had before, where we basically looked at, for a covariate shift, where we had P of Y given X being still the same, but P of X being changed. Here it's that the data generating process is unchanged, but you assume that essentially the labels are the ones that lead to the data generation. And just as before, what you can do is you can just go and reweight according to that ratio. But the unfortunate thing is that unlike before, where we actually had samples from P of X, here we don't have samples from Q of Y, because we don't have the labels on the test set. So it turns out you can do something reasonably straightforward. You basically look at the classifier on f of x. You just train that, right? And then you use basically build an initial classifier, and then you train on that output between training and test set in order to reweight things, and that actually works quite well. So you can, for instance, use directly, the classes. You can also use the scores directly as well. Both work. Now, the last thing before, we get to, the actual AutoML system is we need to look at cases where the data is just, plain malicious and, strangely generated. So let's say I want to do celebrity recognition, and of course, those two gentlemen there are Jeff Bezos and Andy Jassy. And, you can use that for, face recognizer, and it works reasonably well. But then people have figured out, well, actually, it doesn't always have to work. So you can wear glasses that would make Austin Powers proud. And guess what? If I do this and I Photoshop those glasses in, then suddenly my face recognizer fails to work. And the brilliant idea is, and thing is, what they did is they then actually went and 3D printed those glasses, and lo and behold, they were able to throw off a face recognizer also with those glasses. Now, of course, you can do that not just for images, you can do that, for instance, for audio. And so you just add slight amounts of noise, and you do that intentionally in such a way that you can get a very different speech recognizer result. So why does this work? So let's again pick our cute cats. So let's say the training and the natural test set live actually in a very small subspace, right? So it's, for instance, if I look at images, right? So you're all watching this video right now, and you're watching not just arbitrary pixels flickering, but there's structure, right? So there's, for instance, a head that talks, and the head doesn't move in random places across the image. The head stays in the lower right position of that video. Or, for instance, that head always has two eyes and all of that. So in short, what happens is that there is a lot of regularity in the data that you're looking at, and the systems take advantage of that. So basically, they don't become robust to perturbations that are, well, really off that manifold. Now, if I have some unnatural data, then, well, I can break it. And so adversarially robust machine learning has been quite popular lately. And so you'd think, well, okay, wow, this is like a big progress. And actually turns out it isn't, because, well, people have been doing that for a while. One of the original adversarial examples would be spam filtering, because the mail host, well, extends the data set, trains a new classifier, and, the spammer's emails no longer make it. And then spammers go and modify things, and, some emails go through. And then, well, the mail host again, improves their classifier, and you keep on doing this. Now, you might say, well, spam's a special case. No, financial fraud, transactions for anything on, e-commerce site, social media, and so on, all of those very much suffer from it. Sometimes very publicly, whenever Twitter goes and kills, maybe a couple of million, spam bots, some of them publicly, some of them maybe just by default. Well, people realize that maybe they've been had. So one example of what you could do is you could add, highly scoring words or sentences, or maybe even just forge a header because maybe you know that the recipient is Alex. And all of this can be done in order to fool the system. Now, there's actually a very nice, robust formulation. And so basically what you do is you just try to minimize no longer the risk, but the adversarial risk, where you try to, it's basically a minimax setting, where the adversary constantly tries to, perturb the outcomes, and the classifier tries to minimize under that. Okay. So again, in those cases, plain AutoML is not going to cut it, and you need to ask yourself whether, in one of those situations, and whether you need to calibrate for it. Okay. The really last thing that you probably want to be aware of is non-stationary environments. So let's look at the stock price again. So that's for a couple of securities. And, well, the $1 million question, quite literally, is, well, what is tomorrow's stock price going to be? Now, we all agree that answering the question at the red question mark is going to be a lot harder than at the green question mark, because there you have, the future and the past, and then it's just simple interpolation, whereas later on it's prediction. So what this means is that, well, the distribution is non-stationary. Right now we have a bull market, maybe sometimes we have a bear market when everything crashes, like in between March and April. And furthermore, that the distribution is drawn IID. So therefore, if I just, in anger train a classifier, I'm going to get rather poor results. Furthermore, you might end up interacting with the environment. So you might, for instance, download a book in a batch while you go and observe, the training data, then you go and deploy. Online, if you take a class, well, you observe, you predict something, and then, you do a new thing. So this is where you adapt your model based on the environment. You might even ask it to do something. So for instance, if you have Mechanical Turk, you go and you can actually show it some examples of something that you want to have annotated, and then presumably you ought to be able to do better. Or in Bandits, well, you go and, you do something, you learn how to do this better, maybe you have some context, and then, progressively you hope to do as well as the best in hindsight. In some cases, well, the environment remembers what you did. So in reinforcement learning, if it's chess, well, it's an adversarial case. When you drive a car, well, if people are friendly on the highway, it might be more collaborative. Or in some cases, the environment just doesn't care, but will still remember what you're doing. Let's say, for instance, if you're manipulating a pendulum, the pendulum isn't really out to get you, but it might still, respond in certain ways. and remember what you did. So the example would be here for batches, training data, then you build a model and you deploy. Online, well, you go and have one observation at a time, you improve your model. In the bandit case, well, you don't necessarily get to see what all the other bandits would have given you, you just pull one arm. Now, but the bandit doesn't actually remember what you did before. On the other hand, if you have a rhino, this might very well remember it. And so if you have a rhino without memory because it's been, sedated, well, it will happily let you do all sorts of things. But we'll be told if it wakes up and starts to remember what you're doing to it, then you might find yourself at the very pointy end of something. And that's not good. So, as said, in reinforcement learning and control, you get exactly that. You take an action, the environment reacts, you observe stuff, you update the model, and you repeat. So, this was a very, very long overview over basic machine learning problems. I hope it's useful. So this gives you some idea of why you still need to be cautious, even if you have an AutoML system, such that you can deploy this efficiently and, well, more or less automatically. Some of the issues on the list will eventually probably be addressed automatically by an AutoML system. For instance, for the various shift problems, you could easily install something and build something that goes and detects whether the environment has changed. And once that's the case, well, then of course you can go and fix it. So with that, let's take a break and then let's get back to AutoML, to a basic overview of our AutoGluon.